Hello there, my name is Kontoudis and I am a PhD candidate in electrical engineering at Virginia Tech. In this video I will present decentralized methods to implement Gaussian processes in multi-robot systems. This work has been done in collaboration with my PhD advisor Daniel Stilwell at the Center for Marine Autonomy and Robotics. Our group is interested in underwater robotics and specifically in marine applications with multiple autonomous underwater vehicles. We focus on multi-robot systems because they can accomplish tasks that cannot be efficiently addressed by a single robot. Our overall objective is to execute underwater missions by using decentralized techniques towards achieving collaborative autonomy. The research challenge of this work is to seek methods so that Gaussian processes can be incorporated by teams of robots and as a result to facilitate decentralized data-driven probabilistic learning. The major disadvantage of Gaussian processes is the poor scalability. More specifically, GPs require cubic time complexity and quadratic space complexity with a number of observations. In practice, this means that we can use up to 10,000 observations with a regular computer. In multi-robot systems, this number is further reduced according to the number of robots. For instance, with 5 robots, we can use up to 2,000 observations per robot. Additionally, these observations must be communicated. This leads to another major drawback of GPs in multi-robot systems: the communication. Our objective in this work is to synthesize decentralized Gaussian processes for multi-robot systems that are computationally efficient and require as little communication as possible. In the literature, there are 2 major directions to overcome the scalability of Gaussian processes based on local and global approximations. The global approximation methods require global knowledge of the observations for all robots, which significantly increase the inter-robot communications. Therefore, in this work we focus on local approximation methods. These methods entail for every robot the computation of a prediction value based on local observations and the hyperparameters from the training. Now the question becomes how to merge the local predictions of each robot to an aggregated predictive distribution. Several approaches have been proposed for this problem, including the product of experts, the generalized product of experts, the Bayesian committee machine, the robust Bayesian committee machine, the generalized robust Bayesian committee machine, and the nested pointwise aggregation of experts. Out of those, the 2 latter are consistent prediction methods under some assumptions, meaning that as we increase the number of observations to infinity, the methods produce identical results with a Gaussian process. However, GRBCM requires additional communication between robots to enrich local datasets with a global random dataset, and thus we employ the NPI method. Let's take a closer look to the nested pointwise aggregation of experts. Let the underlying latent function produced by the Goldstein-Price equation. Assume that we have 10 robots and that every robot collects observations along the y-axis for every 0.1 margin of the x-axis. For instance, the marked areas of observations of the right image correspond to the robots number 2 and number 6. The inputs of each agent are 1. The location of interest or prediction point, 2. The location that the robots gather their observations, and 3. The local prediction mean vector. The goal is to aggregate the local predictions from the GP experts or robots at the prediction point. The main idea is to form a new Gaussian process using the local prediction mean values and the unknown location of interest. This new GP makes use of the kernel, the cross-covariance, and the covariance. Both the cross-covariance and the covariance are functions of the kernel. The hyperparameters of the kernel are computed during the factorized training, and the kernel is predetermined, say a separable squared exponential. The computations of each robot are 1. The local prediction mean, 2. The local cross-covariance, and 3. The local covariance. Note that all 3 quantities are functions of the kernel and of the observations. Then, after communicating these 3 quantities to the central node, the aggregation takes place. The aggregated prediction mean and variance equations are shown to the bottom. The NPI structure is presented on this slide. First, every robot computes locally 3 quantities based on their observations. The 3 quantities are the local mean, the local covariance, and the local cross-covariance. Second, after every local quantity is communicated to a central node, the aggregation takes place. The main advantages of NPI is first, the maximum number of observations is increased by 2 orders of magnitude, allowing up to 1 million observations, and second, NPI is a consistent predictor with bounded approximation error. However, this is still a centralized method with high computational complexity in the central node especially for large-scale robotics teams. Now, the centralized topology imposes several problems in multi-robot systems. For some robotic applications, including underwater and underground missions, central node communication is very challenging. In addition, there are privacy concerns, as all information is available at a single node. Finally, excessive communication may lead to network traffic congestion. For these reasons, our goal in this work is to make NPI compatible with decentralized and distributed robotic network topologies. The main idea of our work is to utilize local experts or robots without central aggregation, but instead use iterative and consensus methods to decentralize NPI and maintain its advantages. We synthesize our techniques by employing the Jacobi Relaxation, Discrete Time Average Consensus, and distributed algorithms for solving linear systems of algebraic equations. The first technique we propose is termed as Decentralized NPI and employs Jacobi Relaxation and Discrete Time Average Consensus. Jacobi Relaxation is an iterative method for solving the HZ equals B problem, where the matrix H and the vector B are known. The goal is to find the solution vector Z. Each robot has access to one row vector of matrix H and to one entry of the known vector B. The ith element of the unknown vector Z is given as follows. Here Zi superscript S is the value of Z at the S iteration. Omega is the relaxation factor, and Zj is the communicated value from the jth robot. Note that the summation has a huge restriction as it requires communication with all other robots and thus imposes a strongly complete topology. To connect NPI to JOR, here is the equivalence notation. Our overall goal is to compute the aggregated prediction mean. With JOR, every robot knows an element of the vector that is emphasized in the boxed part of the equation. Then we apply the discrete time average consensus, which computes the average of a vector. The consensus law is given here. Aij is the corresponding element of the adjacency matrix, epsilon is the parameter of the Perron matrix, and Zjs is the communicated value from robot J. Note that the sum is over the neighborhood and not over all other robots, and thus entails less iterations before convergence. To connect NPI to DAC, here is the equivalent notation. Essentially, each robot converges to the average of the size of the fleet. To compute the aggregated prediction mean, we just multiply by the number of robots. The aggregated variance computation requires similar steps. Here we show the structure of DEC NPI. Each robot collects observations and computes locally the three quantities of NPI. Then we use the Jacobi relaxation to solve an unknown system of algebraic equations. With JOR, every robot must communicate with every other robot, which leads to excessive communication and may impose flooding if the graph topology is not strongly complete. After JOR converges, we use the discrete time average consensus to compute the arithmetic mean. Finally, provided the size of the fleet, the DEC NPI computes the prediction mean and variance. The second technique we propose is termed as distributed NPI and employs a distributed algorithm for solving linear algebraic equations, or else DALE. DALE is an iterative method for solving the HZ equals B problem, similarly to JOR. Each robot has access to one row vector of matrix H and one entry of known vector B. The unknown vector Z is given as follows. There are two major differences between DALE and JOR. First, DALE can work with weaker and more realistic topologies that reduces significantly the inter-robot communication. Second, DALE computes the vector Z and not just an element of Z. On the flip side, DALE requires the matrix A to be full row rank. Otherwise, there are no convergence guarantees. So the question now is, how can we ensure that matrix H, which in our case is the covariance, is full row rank? In fact, for disjoint partitions of data, and when the robots are distant from their prediction point, the covariance should have 0 rows and columns to indicate no correlation. To address this problem, we introduce the Covariance-Based nearest neighbor method. The main idea is to evaluate the cross-covariance vector to identify close to 0 elements. The cross-covariance vector is termed as k small a and can be computed by all robots under some assumptions. If a cross-covariance element is below a threshold, then we say that the corresponding robot has negligible contribution to the prediction. As a result, we remove their corresponding rows and columns from the covariance matrix and compute the aggregated prediction with a reduced covariance matrix. To illustrate the method, we provide an example. Let a team of 5 robots that are assigned to predict a variable of interest in 50 locations. The first point lies in the area of the first robot, and thus its cross-covariance is the highest. That is 0.7285. The area of operation of robots 4 and 5 is far away from the location of the prediction point, and thus their cross-covariance is almost zero. To this end, we remove the 4th and 5th rows and columns from the covariance, and we proceed the prediction with a 3x3 covariance matrix. Similarly, CBNN applies for prediction points 12 and 50. Note that in most cases the threshold is clear. Here we saw the structure of distemp. The local computations are similar to our previous method, but we also compute the rest local covariance vector elements to introduce the covariance-based nearest neighbor technique that identifies informative neighbors around the location of interest. Only the robots located in the neighborhood space take place to the prediction towards reducing the communications. Next, we employ a projection-based distributed method for solving linear algebraic equations, the DALE. DALE has the same objective to JOR and is concurrently a consensus algorithm. Thus, no averaging is required. Numerical experiments are performed to illustrate the efficiency of our methods. We use real-world dataset of sea surface temperature. We extract 100, 22,000 and 500 sea surface temperature values measured in kelvins from NASA. Out of these values, we use 20,000 observations equally distributed for 7 fleet sizes. The area corresponds to 400 km by 400 km of the Atlantic Ocean, and for demonstration is normalized over a unit square. An example of 10 robots is shown in the middle figure, where each color corresponds to observations from different robots. We employ 6 techniques over 100 prediction points: the regular full GP, the regular MPAE, the DEC-MPAE with complete graph topology, the DEC-MPAE with path graph topology, the DIST-MPAE with path graph topology, and the DIST-MPAE with augmented path graph topology. Each graph type is shown in the right figure. For every scenario, we perform 15 replications to remove the effect of random assignment of data. We use 4 metrics to assess our methods. The results reveal a trade-off between accuracy and communication. DEC-MPAE provides a good accuracy but requires high communication. DIST-MPAE produces satisfactory predictions for small and medium fleet size with much less communication. In conclusion, we propose 2 distributed and computationally efficient GP methods that cover a broad spectrum of multi-robot applications. Additionally, both prediction methods are proved to be consistent. For more details, please check our paper. A preprint and demonstration code can be found in the following web pages. Thank you for your attention, and I hope you enjoy ICRA.